Hello everyone, myself Sridhar and I am from Computer Science and Engineering Department and today my AD topic on differential equations and vector calculus is homogeneous linear equation in PDE partial differential equations. Uh, Introduction to homogeneous linear equation. Homogeneous linear equations are crucial in study of partial differential equations. They are defined as the equation that can be expressed in the form of L of u equal to 0, where L is a linear differential operator. Understanding these equations is essential for solving various physical and engineering problems. It's an homogeneous equation would be in the form of mdx plus ndy equal to 0. Here we can have an example dy by dx equal to x square plus 3y square plus 2xy, where we can put y equal to vx, then dy by dx equal to v plus x of dv by dx. And so we get x into dv by dx equal to 1 plus v square by 2y, where 2v into dv by 1 plus v square equal to dx by x. On integrating, we get x square plus y square equal to px, where this is the homogeneous form of an equation. And a definition of homogeneous linear partial differential equations. So here a homogeneous linear partial differential equation is one in which all terms are linear and there are no constant terms. The general form can be expressed as a of xy into u of x equal to plus b of xy into u of xy plus c of xy equal to 0. Here u is unknown function and a, b, c are coefficients that may depend on the independent variables. Examples of homogeneous linear differential equation, partial differential equation. Here, the equation u of t equal to ku of x is a common example, where the wave equation u of t equal to c square u of x is also fits this category. Both these equations exhibit linearity and are homogeneous. Importance in mathematical physics. Homogeneous linear differential partial differential equations model various physical phenomena such as heat conduction and wave propagation. They provide foundational solutions that can be used to build more complex problems. The solutions are often reveal important properties of the system being studied. Here, there are example exercises where linear homogeneous partial differential equation with constant coefficient are made complex solution to the form. Here u of x of t equal to a into e power minus I of kx minus omega t, where this is an equation where this is the form of homogeneous equation. So where homogeneous equations are very much important in mathematics. And superposition principle. One of the key properties of homogeneous linear equation is the superposition principle. The principle states that if u of 1 and u of 2 are the solution, then C1 u1 plus C2 u2 is also the solution for any constant C1 and C2. This characteristics generally simplifies the process of finding general solutions. General form of second order discrete equations are like xn plus 2 plus a1 xn plus 1 plus a2 xn equal to bn, where xn equal to an a1 lambda 1 and also so on. And boundary and initial conditions. Here, to solve homogeneous linear partial differential equation, appropriate boundary and initial condition must be specified. These conditions help narrow down the infinite number of solution to unique solution. Common types of conditions include Dirichlet, Newman's, and Robin boundary conditions. Method of separation of variables. The method of separation of variables is a most powerful technique for solving homogeneous linear partial differential equations. This method assumes that the solution can be expressed as a product of function, each dependent on the single variable. It transforms the partial differential equation into a simpler ordinary differential equation, where here you can see dy by dx equal to 2x into 2x by 3y square, where 3y square into dy by dx equal to 2x, where 3y square into dy equal to 2x into dy. Here we are separating the variables according to their coefficients, which are like y or x. We are separating y on one side and x on one side and then integrating those. So we get the answer y equal to root over x square plus c. This is uh, known as separation of variables or variable separable. And Fourier series solutions. Fourier series can be employed to express solutions to homogeneous linear partial differential equation with periodic boundary condition. This technique transforms the problem into sum of sines and cosines. Each term in the series corresponds to a mode of the system's response. Here the Fourier series is f of x equal to 1 by 2 into a naught plus summation n equal to 1 to infinite an cos n x plus bn sin 2x. This is the Fourier series formulas, and this is all about the Fourier series solutions. And here, eigenvalue problems. Many homogeneous linear partial differential equations lead to eigenvalue problems. When applying boundary conditions, the eigenfunction obtained are essential for expanding the solution in series form. The eigenvalues provide critical information about the stability and behavior of the system. Here, the inhomogeneous boundary conditions are like in a class, we solve many different types of partial differential equation via separation of variables. However, we only ever solve these homogeneous boundary conditions. So we are starting with a partial differential problem. Dou square u by dou d square equal to c square into dou square u by dou x square, where u equal to u of x y x comma 0 is f of x and u of x comma 0 to 0 of x, where these are the boundary conditions for the eigenvalue problems. Laplace transforms. Laplace transforms can be useful for solving linear partial differential equation, especially when dealing with initial value problems. This technique transforms the partial differential equations into an algebraic equation in the Laplace domain. The inverse transform then yields the solution in the time domain. Green's function. Green's function are instrumental in solving inhomogeneous problems using the solution of homogeneous equation. They allow for the construction of the solution by considering the response to point sources. The method involves integrating the product of Green's function and the source term. Characteristics of a Cauchy problem. The method of characteristics provides a systematic approach to solving first order homogeneous partial differential equation. This method involves finding curves along which the partial differential equation reduces to an ordinary differential equation. The Cauchy problem is a specific case where initial conditions are given along a characteristics curve. Classification of partial differential equation. Homogeneous linear partial differential equation can be classified into elliptic and parabolic and hyperbolic types. Each classification can distinguish characteristics and implementation for the behavior of solutions. Understanding the classification aids in selecting appropriate solution techniques. Stability analysis. Stability analysis of homogeneous linear partial differential equation examines how solutions behave under perturbations. Techniques such as eigenvalue analysis helps determine if solutions are stable or unstable. This analysis is crucial in applications like fluid dynamic and structural mechanics. Numeric methods. Numeric methods are often employed to approximate solutions to homogeneous linear partial differential equation. Techniques like finite difference and finite element methods can handle complex geometrics and boundary conditions. These methods provide valuable insights when analytical solutions are difficult or impossible to obtain. Applications in engineering. Homogeneous linear partial differential equations are widely used in engineering disciplines such as civil, mechanical, and aerospace engineering. They model phenomena like heat flow, vibration analysis, and fluid dynamics. Engineers rely on the solution of these equations to design and analyze various systems. Applications in physics. In physics, homogeneous linear partial differential equations describe fundamental process such as waveform, wave motion, and diffusion. The solutions often reflect the underlying symmetry of the physical systems. These equations are integral to the theoretical frameworks such as quantum mechanics and general relativity. The role of initial and boundary value problems. Initial and boundary value problems are central to study of homogeneous linear partial differential equation. They provide the necessary constant for generating unique solution. The interplay between the partial differential equation and the value shapes the overall behavior of the system. Summary. Homogeneous linear equation in partial differential equation are fundamental to many scientific and engineering fields. Their properties such as linearity and superposition simplify the problem-solving process. A variety of analytical and numerical methods exist to address this equation under various conditions. Uh, Future directions. Research continues in more efficient numerical methods for complex homogeneous linear partial differential equations. And these are some of the references where we got these partial differential equations. These are all the different, what do you call references. And this is all about the homogeneous equation in partial differential equations. And thank you.